Welcome to the day. Let me introduce Professor Bradley de Hobius. Professor Bradley de Hobius has his Bachelor of Science in Physics and Mathematics from the Free University of Amsterdam, a Master of Science in Mathematical Physics from the University of Amsterdam, and a PhD in Mathematics. His research interests are operator algebra, submodular structure, Hilbert spaces, domain theory, category theory, and the notational semantic of quantum programming language. Currently, he is working on noncommutative generalization of mathematical structures using quantum relations as defined by Hilbert. Thank you for your time and consideration. Yes, I let you with the talk for today is operator space model of quantum computing. Thank you.
Thank you very much. Unas palabras en español. Me siento mucho bienvenido y gracias. Su hospitalidad es muy padre. Yo soy de Holanda y trabajo en Austria, pero mi esposa es de México, entonces visitamos México a menudo y estoy muy feliz por esta posibilidad de hablar sobre mi investigación, porque creo que es bueno si puedo establecer conexiones con la investigación en matemáticas en México. Desafortunadamente, mi español no es tan bueno. Entonces, yo voy a continuar en inglés. So I'm going to talk about operator spaces as model for quantum computing. So I will first give a motivation, and we'll talk a bit about what models of quantum computing entail. And an important part is noncommutative geometry, which is a mathematical theory of describing quantum phenomena, and I want to use those methods to construct models for quantum computing. And in particular, I'm interested in operator spaces, and I will use them in several ways. There's also a methodology which is called discrete quantization, in which operator spaces occur. So first, what is quantum computing? So quantum computing is based on the following. So with classical computing, you have that bits which contain all information. The states can be either 0 or 1. But with quantum computing, you can also have states which are 0 and 1. But they can be that at the same time. They can be in a superposition. And because of that, we can obtain quantum advantage of quantum computers. So it means that certain problems, not all problems, but certain problems can be solved much faster than ordinary computers. And this is based on this principle of superposition of states. Now, important is that in quantum computing, just like ordinary computers, the control flow is classical. So what do I mean with control flow? That is in a programming language that you are looking at how to execute conditional statements. So there are if-else statements, but also the order of execution of operations. So for both current quantum programming languages and for ordinary programming languages, the control flow is classical. But the question, is there something as a quantum control flow? And the idea is, why would we like this? Is because it would give us the possibility to obtain a superposition of programs. And that is a very important possibility if you can achieve that, because with ordinary computers, if you have some problem, then often you have to calculate several cases. You first do the first case and the second case and then the third. And because that goes one after another, that takes time. But if you have superposition of programs, then you can do all those cases in a superposition. Hence, it can be done all at the same time, and that would give you a lot of speed up in your computations, and so that would be a nice property to have. But yeah, it's already a question. We don't know exactly what a quantum control flow would mean. But there are some elements which we probably would have. So with classical controls controlled by bits, so if else statement is controlled by a bit in the sense of, okay, we have here a condition, and if it either holds or not, so it's 1 or a 0, which is the value of a bit. And with quantum control, yeah, then you would have control by a qubit. So you get here conditional statements where, yeah, the if is a 0 and the else is the 1. But because you have a superposition of states, then both cases are considered at the same time. And furthermore, you have something as the execution order for classical control that is very definitely defined. So you have one operation, then the following, and then the following. But with quantum control, it's so-called indefinite causal, which means that you can have mixed order of execution. Now, I give an example. And it's based on Schrödinger's cat. So all these examples always boil down to Schrödinger's cat. So here, the idea is with Schrödinger's cat, we have a control bit, and we have a cat in a box. And if the control bit is 1, then the cat lives. If the control qubit is 0, then the cat is killed. And before you measure the control qubit, the control qubit is in a superposition of both 1 and 0, which means that the cat is also in a superposition of alive and dead. And that we can, use this whole principle. So the quantum switch, here we have a control qubit, and here we have a qubit on which we are going to do our operations A and B. And if the control qubit is in position, so in state 0, then we do first A and then B. But if the state is is 1, then we do first B and then A. And hence, if you don't measure the control qubit, the order of operation is in a superposition. And so this is some kind of example of. This is the mathematical formulation of this whole quantum switch. So it's an indefinite causal process. It's also a higher order process. That means, so A and B are processes. Itself, we don't, we don't tell yet what it is. You can fill in any process you want. Hence, it is a process which has processes as input, and then we say that it's a higher order process. And this is a bit a template of superposition of programs in quantum control, because we can have here some pseudocode. If 0, then execute A first, followed by B, and else if 1, then we execute program B first, followed by A.
I'm sorry. I ask a question? But what if there are functional dependencies between A and B?
A and B. Typically they are gates. They are quantum gates, and they don't have a priori.
Okay.
But I think you can indeed consider more general quantum channels, and there might indeed be interactions there. But it's indeed. This is also part of research. If you have these interactions, how can we describe that? Is there a good framework in order to discuss this? And that is something we don't know yet. And I think this work is also intended as a bit a startup to understand this better.
Okay, thank you. Okay, so some recap. If we have superposition of states, then we obtain some kind of quantum advantage, but maybe a better way of obtaining it, even a more
strong version is via quantum control, and hence superposition of programs, but we have no idea how to do this. And it requires a good understanding of these higher order processes and their interactions, which are superpositions, but also perhaps what you were mentioning. Okay, we have to understand it better. And how do we do that? That would be via a model of quantum computing. So the idea of mathematical semantics, or also called denotational semantics, is that if we have a programming language, that we translate programs to mathematical functions. And this is used for several things. So denotational semantics is used for the verification of the correctness of programs. So for instance, there is software which should be without any bug, like in a plane. You don't want bugs in that software. And debugging doesn't guarantee you to get rid of all the bugs. And then denotational semantics offers you methods to really get rid of all the bugs. This is also useful for quantum computing because of the probabilistic nature of quantum computing. It's very difficult to debug. It's also used to study properties of programs, but for this talk, the most important thing is that it can be used to find new programming features or even paradigms. And that is because it gives you a semantic framework which is independent of languages, which means that we have a model and we can tweak the model and we can add extra structure, and that then corresponds to features of your extra new features of your language. And sometimes you can consider structure which you don't know yet to what feature it corresponds, and then it could be a new feature, and in this way you can discover new features. So models consist of categories. I don't know how much knowledge, pre-knowledge you have on categories, so I decided to include some slides on categories. So the starting point is that in mathematics you have often certain structures you're interested in and maps that preserve that structure. So examples are sets and functions, but also groups and group homomorphisms, posets, monotone maps, topological spaces, vector spaces, etc. And it turns out that there are often constructions for all these different structures which are kind of the same. So for instance, there is the set theoretic product of sets, there's the direct product of groups, there's the product of posets, the product of topological spaces, product of vector spaces, and it turns out they all satisfy a similar property, namely we have here this product, then there are projection maps which preserve the structure, and then if you have maps into the vectors which preserve the structure, then there is a unique structure preserving map into the product. And this suggests that there is some deeper structure to talk about mathematical structures, and that's exactly category theory. And the rough definition of categories consists of a class of objects and a class of morphisms between these objects, and then some axioms. And often these structures and structure preserving maps yield categories. So for instance, we have the category set of sets of functions, category groups and group homomorphisms, posets, topological spaces, Hilbert spaces, and category of Banach spaces and linear contractions. And more interesting, there is even a notion of a morphism between categories, and that's called a functor. And some examples are, if you have the category of posets, then you have the forgetful functor, which if you have a poset, you take just the underlying set, forget about the order. You have a similar functor for topological spaces. But perhaps a more interesting example is in topology, you have the homology groups, and those turn out to be functors. And so that's a cool aspects of category theory. And even categories themselves form a category. Categories and functors form a category of categories. But yeah, you have to be a bit careful with Russell's paradox. So there are some things you have to be careful with. Yeah. Now, the idea of mathematical semantics is so a model then consists of category and a compositional function from your programming language to this category, which translates programs to morphisms of C and data types. So programs often have a data type like integers or booleans, and they translate to objects. And then often, if we have some type, we can construct new types via something called type constructors, and those correspond to functors. Now, some examples of type constructors which are very important. We have, if we have some data where we have an integer and a boolean, then we want to find, we describe this data then as the combined data type integer boolean, pair of an integer and a boolean, and that's done by the pair constructor. And we have also, if we have some program which sends data of type A to type data of type B, for instance, if you have the floor function which sends real numbers to integers, and then that program itself has the type function type A to B. And this is also necessary to describe higher order processes. Now, how to model these type constructors? So we already saw the definition of a product. A category in which the products of two objects exist is called Cartesian. And the product then turns out to be a functor, and this is used to describe these pairs. And for the function types, in order to define how to model that, first consider ordinary sets, and we can then form the exponential sets of functions from y to z. And that has some nice properties. There's an evaluation map that if we have such a function from y to z and we have an element in y, then it can map both to an element in z. And if we have a function from the product of x and y to z, then we can form a function het f from x to this function, this exponential set. And it turns out that these maps are kind of each other's inverse, and that gives us a bijection between the set of all functions from the product to z to the set of all functions from x to the exponential map. And this whole bijection is called currying. And this is the definition of a Cartesian closed category. If you have a Cartesian category, then it's called closed. If for any two objects, so here the objects are not necessarily sets anymore, they are just objects in the category you are considering. If we have such a bijection, so here this is the notation of all morphisms in the category between those two objects. If we have such a bijection, then this object behaves a bit as an object of functions from y to z, and then we call this Cartesian category closed. And this is exactly, so examples are sets, posets, and the category of categories. And this is exactly the functor we use to model function types. Now, we have here the following diagram. So we have here correspondence between logic, or to be precise, intuitionistic logic, languages, programming languages, where you have types and you have these higher order functions, and Cartesian closed categories. And this is called Curry-Howard-Lambach correspondence. So any proof corresponds to a program which corresponds to a morphism here. And this is this whole idea of denotational semantics, that it's independent of the language. You can here add structure, and that should correspond then to some feature here, or you can weaken down this, and then you have to weaken down your operations here. And yeah, that's a bit the whole magical triangle for denotational semantics. Okay, so recap. Denotational semantics, that is the translation of programming languages to categories. And yeah, this is independent of specific languages. Pairs are modeled by products, higher order functions by exponential objects. And if we add structure on the categories, then it corresponds to new features on the language. And sometimes features we are not even aware of, and then, hey, we have a cool new feature. And if we weaken down the categories, then we get weaker features here. And now it's the question, what do we need for quantum computing? So, first of all, we need to know what is the appropriate logic for quantum computing. And it turns out that there is a logic which is source sensitive, and it's called multiplicative linear logic. And that means that, for instance, you have the statement, okay, if I have one apple, and with normal logic, okay, if I have an apple, then I can make a pie from the apple, but I can also eat it. And in classical logic, that can happen at the same time. But if in daily life, if you have one apple, no way that you can eat it and also process it in an apple pie. And multiplicative linear logic tracks this information. And that's important for quantum computing because in quantum computing you have the no cloning theorem, so you have this resource sensitivity. Now, then there is an extra operator which you can add. It's called the bang operator, and that expresses what information can be copied and what not. And that's also important for quantum computing, because in quantum computing you have quantum information, but you also sometimes have classical information, and the classical information can be copied. And so you need an operator which keeps track of what can be copied and what not. So this multiplicative exponential linear logic is the appropriate logic for quantum computing. Now, how to model this logic? So first of all, we cannot use products anymore, because with products, there is some property which allows us to copy things, but we are not allowed to do that. So we have to replace the product by a monodal product. And that's some concept in category theory which generalizes the ordinary products. We call a product symmetric if the monodal product of x and y is the same as the product of y and x. And many monodal products are induced from tensor products on well-known structures. So for instance, we have the tensor product on vector spaces. And there is some universal property. So first of all, we can span it by elements of this form, which we call elementary tensors. And then if we have a bilinear map from the ordinary product to Z, then there is a unique linear map to the from the tensor product, such that this diagram commutes. So if we take from these pair x and y, we first take elementary tensor, and then we apply the linear map, then we should get back the bilinear map. And this defines the tensor products on vector spaces, and this is an example of such monodal products. So we say here that the tensor product linearizes bilinear maps. And similarly, we have for Banach spaces, we also have a tensor product called projective tensor product, and that linearizes so-called contractive bilinear maps, and that's also an example of monodal products. Now, if we have a monodal category, then we have a similar property which generalizes this exponential sets. So we have here a similar condition, and we don't speak anymore of exponential objects, but of internal homes. And an internal home also behaves a bit like a set of functions between two objects. But the biggest difference is that here we now have the tensor product or the monodal product instead of the ordinary product. And yeah, this is then used to model function types in multiplicative linear logic. And now we get a similar diagram. So here, if we consider so-called linear higher order programming languages, then it corresponds to multiplicative linear logic. And on the semantical side, with symmetric monodal closed categories. Now, some examples. So I already mentioned the vector space tensor product, which has as internal home all the linear maps from Y to Z. Hilbert spaces has as internal home, you take here dual of a Hilbert space and you tensor it with Z. And Banach spaces has the Banach space projected tensor products, and here the internal home are all the bounded linear maps from Y to Z. So if you also add this Banach operator, then you need a certain functor from C to C. The technical condition is that it's a comonad to model this Banach operator. And if you have your category is so-called locally presentable, that's quite a technical categorical concept, so I don't give the exact definition. But if your category is locally presentable, then you can easily construct such a functor which models Banach. And it's a theorem that the category of Banach spaces is locally presentable, hence it is a model for multiplicative exponential linear logic. Now, there is some issue for quantum computing because you need objects in your category which can represent quantum systems like Hilbert spaces. So often what people do is they consider a category Q, which consists of these objects representing quantum systems, and you take as morphisms first order quantum processes, but you need a symmetric monodal closed category. So then there are some categorical constructions which embed Q into a symmetric monodal closed category, and then you get a nice categorical model. But the problem is, so it works for first order quantum computations for basic quantum processes, but these higher order quantum processes, which are important for these examples as the quantum switch, are not properly captured in such a model because these higher order processes are modeled by categorical constructions, and these categorical constructions cannot capture superpositions properly. And yeah, alternatively, you can work with Banach spaces because Banach spaces, Hilbert space is an example of a Banach space. But the problem is that the projective tensor product is not the same as the Hilbert space tensor product. So this is also not a good model for quantum computing. So we have to find something else which models this higher order maps in a nice way so that we can discover how to properly describe quantum switches. So a recap, quantum logic, that's this multiplicative exponential linear logic. So yeah, it's a different logic than the usual quantum logic of Birkhoff and von Neumann, in case you heard also of that kind of logic, but for quantum computing, this is the appropriate logic. And models are symmetric monodal closed categories. I've got to put closed with a Banach functor. And models should contain objects which represent quantum systems. And the current models don't do that. Now, my idea is to use, or my idea, I work with other people, to use the framework of noncommutative geometry to find good models. Now, what's non-commutative geometry? The first step is what is an operator algebra? That's algebra of bounded, that's the same as continuous, linear operators on a Hilbert space. And yeah, there are some special classes of which you might have heard, C-star algebras and Neumann algebras. And quantum systems can be described by operator algebras where the observables are exactly the self-adjoint elements. Now, the nice thing of operator algebras is that you have, if you have a classical system, normally that's described by a phase space, which is typically locally compact Hausdorff. And observables are exactly real valued continuous functions on this phase space. Now, turns out that in operator algebras, you have a theorem called Galvan's duality. And it states the following, that if you have a locally compact Hausdorff space, then you can look at the continuous complex valued maps, which vanish at infinity, and that's exactly a commutative C-star algebra. And all commutative C-star algebras are of this form. And now, if you look here, what are here the self-adjoint elements in this algebra? Those are exactly the real valued functions. So it follows that also classical observables correspond with self-adjoint elements. So we can both describe quantum systems by operator algebras and classical systems. In both cases, the observables are the self-adjoint elements, but in the case of classical systems, you have a commutative C-star algebra. So that's the nice thing of operator algebras. Both classical and quantum are united in the same framework. Now, the idea of non-commutative geometry is to exploit this whole idea, and you want to describe quantum phenomena in terms of operator algebras. And it's based on the observation that often, if you have some quantum phenomena, it has a classical counterpart. And then you have the notion of quantization, that is, that you try to find non-commutative generalizations of the structures of some mathematical structure. And that's often non-commutative structures in terms of operator algebras. And yeah, if you then have quantum phenomena, you look at classical counterparts, you look at the structures which model this counterpart, you quantize these structures, and then you get often a natural model of the quantum phenomena. So that's the idea. And the most beautiful example of such a thing is the non-commutative standard model. So in physics, you have the standard model, which describes all fundamental forces except gravity. And Alan Kohn, he used quantization to find a non-commutative version of this standard model. And it turns out that this non-commutative version also describes some modified version of gravity. So that's very promising. Now, non-commutative geometry comes with a whole dictionary of mathematical structures and their generalizations. So we are interested in Banach spaces and operator spaces, but also in sets. What is the non-commutative generalization of a set? So what's an operator space? That's basically a closed subspace of the space of all bounded operators between two Hilbert spaces. Now, and it's a bit complicated to define what its morphisms are. So first of all, you need to consider matrices which have values in your operator space. And these matrices get a norm, obtain a norm. And then if you have a map between operator spaces, then we can also define a map between the matrix versions. And then we say that a map between operator spaces is completely bounded if each phi n is bounded and the norms, the supremum of all those norms is finite. And we say that it's even a complete contraction if the completely bounded norm here is smaller than or equal to 1. Now, so the idea is, okay, we have Banach spaces which form a model of multiplicative exponential linear logic, but it's not a good model. So since operator spaces are often regarded as non-commutative Banach spaces. We are going to try to make a model of operator spaces instead. And it turns indeed out that the category of operator spaces and complete contractions is symmetric monodal closed. And this is not something I found out. This is already known by all the people who founded this field of operator space theory. So the monodal product is the operator space projective tensor product that's defined in a similar way as this Banach space projective tensor product, but where that product linearizes contractive bilinear maps. Here we have to take completely contractive bilinear maps. And then the internal home for Banach spaces that's given by bounded operators from x to y, but here we have to take the completely bounded operators. So basically operator spaces is the same as Banach spaces, but you have to slam the word contract completely in front of everything. And yeah, then you also need to model this bang operator, and together with Vladimir Zantjev, I found that this category is locally presentable, so it's a difficult condition, and hence it's a model for the logic we want to do, and hence turns out to be a good model for quantum computing. How are we doing with the time? Okay. Now, some nice thing here. We have, so often if you quantize things, it's similar to the classical case, but some things pop up which are non-classical. And for operator spaces, you have something called, it has a very weird name, how to pronounce it. I learned it from my PhD supervisor. You say it's a Norwegian name, Hokrup, I think. Yeah, that's what he told me. It's non-symmetric. It linearizes also some class of bilinear maps, and yeah, it has not a Banach space counterpart. And there's an important theorem which also found by all the operator space people. The whole thing is it tests causality. So, for instance, the quantum switch that can be linearized by the projective tensor product, but not by the Hokrup tensor product. And then if you look at the theorem, that if it would be linearized, then you could write it in the form of something which depends on A after something followed depending on B. So this suggests that if you could linearize it by this tensor product, then we can describe the quantum switch as something in a definite order. But yeah, it's an indefinite causal process, which is some mixture of orders of execution. And yeah, it turns out that we cannot linearize it by the Banach, by the Hokrup tensor product. Hence, we cannot write it in a definite order. And that's exactly what you would expect. So we expect that we can discuss this in definite causal processes like the quantum switch in terms of operator spaces. Now, some things are missing. So we don't have a concept of recursion. We don't know how to do that, and that would also be powerful because then you can easily generate superpositions of programs. Now, recursion is typically modeled by fixed point theorems, so maybe we could use the Banach space fixed point theorem, but already for Banach spaces that doesn't work so nicely. There are some other options, but more interesting is some other quantized models. And that is using the non-commutative version of a set, and it's called the quantum set, which is essentially a set of finite dimensional Hilbert spaces. And you have then also a generalization of a binary relation between quantum sets, which assigns to every Hilbert space, or Hilbert space in a quantum set is called an atom. It assigns an operator space to each pair of atoms. We call the category of quantum sets and quantum relations, we call it QREL. There's also a description in terms of operator algebra. So every quantum set induces a sum of algebras which are isomorphic to a matrix algebra. And then quantum relation corresponds to an operator space between these two Hilbert spaces. Now, with ordinary relations, we have something as opposite relation, and we can also order binary relations. And turns out also that quantum relations can be ordered, and there's opposites. And now the whole idea of discrete quantization is that if we have some mathematical structure, then it's often defined in terms of sets, binary relations, and constraints in terms of this opposite operation. We call it the dagger and the order between binary relations. And then the idea is, okay, if we have some structure we want to quantize, we replace any set by a quantum set, any relation by a quantum relation, and we require that the same conditions hold. So for instance, if we have a function that can be described as a relation satisfying these two inequalities, and then a quantum function between quantum sets is defined exactly in the same way. Now, quantum sets and quantum functions also form a category Q sets, and this category of Q sets, quantum sets, forms also a model for multiplicative exponential linear logic. Now, we have also, we can capture concepts as reflexivity, transitivity, and symmetry in terms of these constraints. And then we can also define what reflexive and transitive quantum relations are. And hence we can define also what a quantum graph is in this way, and also what a quantum poset is. It's just a quantum set with a reflexive, transitive, antisymmetric quantum relation, just like the classical case. And now it's a theorem of André Cornell, Mike Wislov, and I, that the category of quantum posets is symmetric non-model closed. Now we have this general pattern that if we have a Cartesian closed category, we apply discrete quantization, and then we get a model QC, a category quantum QC, which is a model of multiplicative exponential linear logic. And this category often has the same properties, but proving that these properties hold is a bit hard. And yeah, then the idea is that recursion that can be modeled by fixed point theorems. Classically, that's done with CPOs that are posets in which every increasing sequence has a least upper bound. And there's a fixed point theorem for these posets, and hence it can be used to model recursion in ordinary programming languages. Now, together with André Cornell and Mike Wislov, I use discrete quantization to quantize CPOs, and then we get quantum CPOs, and that turns out to be a nice model for quantum computation, which supports recursion. Okay, now I skipped some things about quantum graphs. But yeah, the bottom line is, so we found several models of non-commutative, several non-commutative models in terms of operator spaces. The most interesting are category of operator space and this category of quantum CPOs. One uses operator spaces as objects, and we can discuss causality there. And quantum CPOs uses operator spaces as morphisms, and we have support for recursion. It would be nice to combine those features in one single model where we can discuss recursion and causality, and that would give us a nice model where we probably can talk about quantum switches in a structured way. So yeah, there are some things we have to do. So maybe a combination of both principles can be done by modeling recursion, by restricting to some nice class of operator spaces called dual operator systems. And for QCPO, there is something we can do which requires quantizing topological spaces. And some step towards that is done by Gesa Gensha and me, where we try to quantize complete lattices, because the topology is in particular complete lattice. And yeah, with that, I would like to finish. Thank you for your attention.
Anyone has any questions? Online? I have a question about the recursion because in some language programming languages there are some called tail recursion, so you can avoid the effect of infinite recursion because you are using a linked list to do that recursion. How can you model that?
Garbage recursion?
Tail recursion, because you are adjoining the tail operations instead of doing the recursion.
Okay, yeah. I have worked mainly with Vladimir Samtsev and Mike Mislov on full recursion. And I don't know exactly how to model those kinds of recursions, but yeah, there's also something called guarded recursion. That's also a weaker version of recursion. That might be something we have to resort to, but we didn't look at it because we tried to go for the strongest version of recursion which we are aware of, and that's recursive types. So in these models, you have the types and you have the morphisms. So the objects are the types, the morphisms are the programs, and you have recursion of programs, but you have also that you can define types in a recursive way. And that's a very strong version because it implies that you have also recursion on the programming level, on the programs level, so on the morphisms. And so we have been looking at that, and this whole category of quantum CPOs. It supports this recursive types, and hence we choose to try to get a complete picture there rather than to look at weaker versions of recursion. But there are some problems here, so maybe we have to resort to weaker versions of recursion. And I'm happy to learn more from you about that because I have not looked at the recursion.
Some time. The other question is about the different type of languages, for example, the functional languages like Haskell.
Yeah.
So what do you think about the similarities of this framework that you are proposing?
So yeah, I kept a lot of details a bit under the cover, but typically all the quantum programming languages which are studied the most are functional programming languages. So actually we looked in particular to a language which is called Proto-Clipper M, and yeah, it's a bizarre name. I don't understand why they called it like that. But that's a language which is based on, which is embedded in Haskell. So you have the language Clipper, and they wanted to have a language which is functional, and then they thought, okay, yeah, we have Haskell, so we design a language inside Haskell. But then you have the problem that the data types of Haskell are classical. There are no quantum data types, so you cannot. That doesn't work nicely. And then they came up with a version of Clipper which is no longer embedded in Haskell, and that's Proto-Clipper M. And yeah, we use that a bit as our inspiration for finding models in terms of quantum CPOs. But yeah, generally, the thing is, this coworker of mine, Gesa Dencha, he used to be in programming as well, and he said when he was very drunk, he told, I met him at a conference the first time, and he got drunk, and then he was like, yeah, in the future, will be clear clear distinction between good programmers and bad programmers, and the distinction will be whether you can program functionally or not. So
That's super extreme.
yeah, and he thinks that that's important. But for quantum programming, the thing is, it's very difficult to keep track of bugs, and functional programming forces you to be aware of your types and
and the relation between the
and
the objects.
And the thing is also, I have this whole triangle of logic, programming languages, and categories, and that also always assumes functional programming languages because that fits very nicely in the mathematical framework, and we don't know how to model.
Another type of programming language. Okay, thank you. So we finished the topic.
Thank you very much.